Welcome to this project on support vector machine classification. Support vector machines are extremely useful and extremely powerful, especially on small complex data sets and medium-sized sets. So what they're aiming to do is to find a decision boundary. In classification, obviously they're aiming to fine-tune a decision boundary between different classes of things. So what we're looking for is a hyperplane, which is effectively acting as the decision boundary. What we're trying to do is effectively create a street or a classification boundary between two groups or three groups or however many groups of points or observations. So this is the mathematics involved. There's a whole other presentation, so I won't go through this in detail, but it is good to illustrate how powerful this can be. So here is the hyperplane, here the decision boundary, and these points which are closest to the decision boundary are known as the support vectors. The further away the points are from this decision boundary, the further off the street, as it were, that they are, and the least useful they are to the algorithm to learn about the decision boundary. So if I show you with the iris data set, here is the just general scatter of points. So as I talked about this in the neural net project, basically the iris data set is a small and very clean data set. It's about some iris flowers which can easily be categorized into one of three classes according to sepal length, sepal width, petal length and petal width. So you can see here how effective the support vector machinery is at deciding the decision boundaries. Could be a little bit better here, but basically the points are very intermingled around the decision boundary, so it's hard to do. But here you can see much more clearly how effective support vector machines are. So if I take you to the code of what I created, support vector machines use a kernel trick. Some of the more common ones are polynomial sigmoid. I daily need cross-validation, grid search, and also for the input to be scaled prior to using the support vector machinery. So having downloaded the data, imported the library, I created various plots relating to this iris dataset. So you can see here, so as we mentioned above, two of the classifications are a little bit blurred, but you can see, for example, if we highlight just 2 out of the 3, how effective the boundary is. This is the support vector machinery in action. This is the hyperplane, the decision boundary, and these are the support vectors here. I mentioned about scaling, and it is very important prior to doing support vector machine classification, because you can see how much clearer the situation is with scaling, because obviously these are the 3 points on the decision boundary area which will act as support vector machines, whereas this blue dot is actually near but not as near as the others. Outliers are obviously a key function of any analysis. This type of outlier may well be an erroneous piece of data because it's way away from the main group that it belongs to, whereas this type of outlier is exactly what support vector machines were designed to deal with. I mentioned above about fine-tuning, and you can see how important just playing around with the different parameters is for letting the algorithm work at its optimal efficiency. So, for example, C equals 100, you can see a much clearer picture of what is going on around the decision boundary. And these are plots.